Hello and welcome back. This is Systems Design 522, the Fundamentals of AI, taught at the University of Waterloo in the fall of 2023. And this is Lecture 6, the second part of talking about the kernel trick. Okay, so where were we? So we'd been talking about support vector machines, which were sort of a way of doing classification where we've got two things going on. One of them is we want to make sure that instead of just a classification boundary, we've got a line that separates our data sets. Instead of just any line that separates the data sets, I want the line that separates them the most, what does the best job of separating them. And the way we quantified that was if you have two parallel, you have this margin that sort of separates the two, and you want that margin to be as big as possible. We did a bunch of math showing that that can be turned into a constraint satisfaction problem. And then we sort of showed two versions of that constraint satisfaction problem. We showed sort of the basic, the primal version, which is sort of, hey, we want to minimize the weights because that turns out to be the thing that maximizes the margin. But then we also want to make sure that it classifies things well. So we make sure that that all of these, like this particular line, omega x plus b, that's omega x plus b is going to be our dividing line. But we want to make sure that for the positive ones, for the positive examples, the examples with yi being 1, we want to make sure that that's bigger than 1. And for the negative examples, we want to make sure that they're smaller than -1. Right, so we turn that all into an equation. We said, hey, we're going to turn this into a constraint satisfaction problem. We want these scaling factors here to be greater than or equal to 0. And what it'll turn out will happen is that whatever constraints, whatever sample points are right on the boundary, they will have alpha values that are non-zero. All the other ones will have alphas of 0. We can ignore them. They go away. We did some substitutions. We got an alternate version of it that we called the dual form. But yay, we have these support vector machine things. And then we have a bunch of tools to solve them. Go and find these alpha values. X's are our input data points. Yi's are our desired output data points, either +1 or -1. And then we just go ahead and solve it. And then when I have a new data point coming in, then all I need to do is take that new data point and do the dot product of that new data point with all of the other data points that have non-zero alphas. Sum that all up, and that's my new dividing line. Cool. Okay, fine. But then the thing that was pointed out is, well, we don't have to do this on the raw data. Just like with the perceptrons, doing things on the raw data is very limiting. You can only make linear decision boundaries. But then instead of doing it on the raw data, we can compute some other data. We can compute features of that data. So we compute these phi's and then just do exactly the same thing. Exactly the same math, exactly the same thing. We're just doing it on the features rather than on the raw data. The big thing that we focused on in the last class was what we call the kernel trick, which was a way of saying, well, hold on a second. The math going on here is just dot products between these the features for one data point and the features for another data point. Math going on here is just the dot product between features of one data point and features of my new data point. The interesting thing that this implies is it might be possible, and it turns out that it is possible, to, instead of computing all the features, we don't bother computing the features of our data. We just choose some other function that sort of implicitly defines a bunch of features and does the dot product. Right, so these are the kernel functions, and what they're going to do is they're going to say, well, fine, if I just do this, so I'm computing the kernel functions on my raw data, but that's the same as computing all of my features and then doing the dot product in the features. And this now means that I could have hundreds of thousands or millions or an infinite number of features. It doesn't matter. I'm going to be doing the linear decision boundary in the feature space still, but I don't actually have to compute the features. Well, so that gives us the kernel trick for support vector machines, nonlinear support vector machines. We're still finding the optimal line in that high dimensional space, but we never actually have to compute it. The high dimensional space being the feature space. Okay. All right. So one interesting thing that we then sort of pointed out about, well, why is this so well, why does this work so well for particular kernels? And this particular kernel, the Gauss, which is just take the distance between points and do a Gaussian where that based on that distance. So that'll be this is a kernel where you'll get a value that is 1 if I'm comparing a point with itself, but then the farther that point gets away from, the farther these 2 points get away from each other, the smaller and smaller this value will be. If I sort of used that kernel, then I got this as my nice little decision boundary, which is, that's kind of a nice classifier. This is a classifier, well, hey, okay, these are the data points it was trained on, the red dots and the yellow dots, and then the blue dots and the green dots. The yellow dots are the support vectors. Those are the ones that it said, oh, okay, alpha is going to be non-zero for these points. So in the weird infinite dimensional space that these decisions are being made in, those are the points that are on the boundary of that weird infinite dimensional space. Fine. We're just going to plot them here in the original two-dimensional space. But because we know that when I'm trying to classify a new data point, and that's how I drew this graph, is I just took each individual data point in this whole space, and I said, okay, what would the classifier output for this data point? And so that's use this equation here. And in theory, what I should do is take my data point, compute all the features of that data point, do the dot product with, xi's, that's over these green and yellow dots. So the sum is over the green and yellow dots, because those are the only ones for whom alpha is non-zero. So I compute all the features for the yellow dots and the green dots. That's these. And then I do the dot product between my new data point. I compute its features, and then do that dot product, and then do this weighted sum, add b, and then that result, that's what gives me the color that I'm plotting here, right, on this sort of axis here. But of course, with the kernel trick, I don't actually have to compute these features. I don't have to, especially, and with this particular kernel, it turns out there's an infinite number of features that we're implicitly doing there. The only thing I do instead is say, oh, okay, I'll just compute this function, and that'll sort of implicitly do everything in this high dimensional space. But now that I can look at this function, I can say, well, hold on a second. That means that whatever my decision boundaries are, these are going to be weighted sums of Gaussians centered around each of these points, right? Because this kernel is being generated with this, right? I'm going to have a Gaussian that's centered at this point, at this point, at this point. The yi is just going to be either +1 or -1. So for the green kernels, this is a Gaussian that goes away from the page, and the red one comes towards us. And then alpha, because again, we know alpha is either 0 or greater than 0. Alpha says how strong that Gaussian is, and then we add it all up. So we know that our decision boundaries are always going to look kind of like this. Okay, so this is also a reason why, decision surfaces are going to be like this. If I had to draw a line through this exactly where this sum equals 0, yeah, it's going to be some weird boundary that comes sort of down through this and up and over exactly where this is exactly 0. But we also have this opportunity of saying, hey, if I do this math and I get a value near 0, something's probably gone wrong. This is an ambiguous point. Maybe you want that as an option for your output. You're always going to have systems that sort of look like that. Right? It's always going to go down to 0 as we get farther away, go down to b as we get farther away. All right. And I did note, yes, fine. You can use any distance measure. You don't have to use Euclidean distance. You could use the L1 norm. You could use some other distance measure. Anything where you've got some sort of sense of distance as you get farther away. And for different data, you might want to use a different sort of sense of, what counts as one data point being farther away from another data point. That said, vast majority of the time, just use Gaussian, but also make sure you've normalized your data. As pointed out ages ago, if we had one of these axes that was like 100 times bigger than the other one, then the distances on that axis are going to be way more important than distances on this axis, and it's just going to spend way more attention to this axis than that axis if you had some sort of scaling issue. And that's why it's pretty common to just normalize your data before passing it into these sorts of algorithms. Cool. All right, so that's all review-ish or summary. One big thing I really want to focus on for this, as we're sort of playing with this more, what happens when the data overlaps? So here's, we're going to use exactly the same setup, exactly the same learning, but let's use this data. Please draw a line that will separate that data into classes. That seems like a difficult task. What happens when we throw this algorithm at it? Well, there are a couple free parameters in this algorithm. Okay. But let's leave everything at the default right now. Okay, we've got two free parameters to worry about at the moment. One of them is this gamma. So this how spread out is this Gaussian. And then the other one is the cost, that C variable, that's saying how bad is it for a line or a point to violate the boundary. Those are our only parameters that we have at all in this process right now. So I'm going to leave those both at the default of 1, which is pretty good defaults if you've got normalized data. So cool. And here's what it does for our decision boundary. Okay, we've got, all right, that's not bad. We've got, again, I'm plotting in yellow the support vectors, so the points whose alpha is non-zero. I'm plotting those in yellow and green. The other points are in red and blue. And cool, all right. That seems like a reasonable-ish boundary. What happens when we play with the parameters? So here's what I'm going to do is I'm going to play with the cost first. I'm going to reduce the cost and say, all right, it's okay. It's more okay for points to cross that boundary. Okay. Now we get a lot more points that are sort of crossing that boundary. We get a lot more support vectors. Basically, any point that crosses the boundary is sort of by definition going to be one of your support vectors. So you're going to have a lot more of those. But also still seems fairly reasonable boundary. Let's increase the cost and start saying, hey, it's really, really bad if points cross the boundary. And so this is sort of pointing out that, hey, we can get some pretty complex looking decision boundaries. Nothing says that we have to, have everything grouped together. This is saying, all right, I'm making a little tiny group up here that's, hey, everything over here we're going to count as in the red category instead of the blue one. These don't have to be connected. It can go ahead and make very complex boundaries. Again, it's still linear in that infinite dimensional space that is implicitly defined by the kernel, but fine, being linear in infinite dimensional space, it's very nonlinear in this smaller space. And then we can go also even more extreme, and we can say, all right, so let's increase the cost even more. This is up to a cost of 1,000. Sure, we have this parameter. With a very high cost, it becomes a lot like the sort of the extreme version of do not ever have any points cross the boundary. Okay. All right, so that's one thing we can do. But another thing that we can do is we can adjust gamma. We can adjust the size of these Gaussians. Okay, and increasing gamma. If this was written in the sort of the normal form of a Gaussian where it's like the difference squared divided by 2 sigma squared, so gamma is sort of 1 over 2 sigma squared, and so increasing gamma is the same as decreasing the sigma for the Gaussians, decreasing the width of the Gaussians. And you can sort of see that here, is that I've increased gamma to 5, it used to be at 1, and now you're seeing, oh, okay, this is clearly what's happening, is we are getting these nice, it's every data point is really only telling information about nearby data points. That's, I guess, another way to phrase that, and we're only really saying things about very close nearby data points. Okay. Fine, we can do the same thing and adjust the cost as well at the same time. So fine, all right, there's a different decision boundary. Here's a different one. Here's a different one. Okay, so we have these, like lots of different ways of dividing these data points. And really the only thing that's really happening here is now each of these different support vector machines that we've created, when I give them new data, are going to do slightly different things. They're all going to do pretty darn similar things for points that are sort of nearby. So like a point in here is going to do pretty much the same thing on all of these different ones. But in the edge cases, these can start behaving very differently. Okay. Cool. So we're just going to we'll start with that little bit of intuition about what happens when we adjust these parameters. We will continue to talk about this. One thing that came up is it always possible to perfectly classify? Could we, given, maybe if we stared at these things, are these perfectly classifying? And even if they are for this, are there, so, all right, perfect, certainly this one right here, there's a data point that is not being correctly classified in this bottom one down here. Right. So is that happening? Is it always possible to adjust parameters such that you get a system that perfectly classifies? The answer to that question is yes, but it's not a very useful solution. So what I've done here is I've just made gamma really, really, really big, which is equivalent to making sigma very, very small. So making the width of the Gaussians very, very small. And in fact, they're so small that you can't even see them. And if you make those Gaussians really small, then the classification is literally just going to be, well, the points that are right near the points in my data set, I'm going to classify the same as the points in the data set. Right? They're just a bunch of little tiny Gaussians being added up there. We can see that a little bit better if I'll make the Gaussians just a little bit bigger, and you can sort of see a little bit better about what's going on here. Yep. So yeah, any of these points, fine. Those will get classified as blue. Any of these points classified as red. Anything else, meh. It'll be some number near 0. Now, of course, it won't be exactly 0. If you want to sort of set this up nicely, you could, if it's just, if I choose a point like here, those Gaussians don't drop to exactly 0, or it's going to be some value here that's going to be near 0, but probably slightly positive. And if I did the same thing over here, it'd be near 0, but probably slightly negative. What I've ended up with then, if that's how I'm using a support vector machine, I've basically turned it into a lookup table, and doing something like a nearest neighbor lookup. Okay. And that's something we mentioned really early on with the perceptrons. Yes, I could make any data, if I had the right features, I could turn this into a lookup table, and that's exactly what we've done here. Okay. So if you set your parameters in this sort of extreme way, you get a lookup table, and it does something like a nearest neighbor algorithm for new data points. So if a new data point comes in, it's sort of like, well, which one, is it closer to a blue point or closer to a red point? It's not quite that. It's actually adding up the Gaussians at every single point, but you can sort of think of it that way. So it's kind of neat that this sort of, in the extreme version, turns into an extreme version of the classifier. So that's sort of in the scope of things that we could make this thing do if that's what we wanted. Probably not what we want, though, because that's not a system that generalizes very well. It's also very expensive in that every single point is now a support vector, so I'm doing a comparison to every single point, but fine. So we need some sort of practical guide or some sort of, well, what approach are we going to be using when we go and apply this, because we've got some parameters to play with here. So, practical guide to using support vector machines. Step 1, just use the Gaussian. Just use sometimes it's called Gaussian, sometimes it's called radial basis function, Gaussian radial basis function. It's the default, just use it. Every now and then, something else might be more suited, but that would be a situation that is incredibly situation specific, where you know something about the structure of your data to say, it's not, points nearby shouldn't be something like a Gaussian blob. There's some polynomial that would be better or something. Fine. That's incredibly rare. Maybe you want to choose some sort of distance measure rather than Euclidean distance. Sometimes people will, in very high dimensional spaces, people will use just the L1 norm. So instead of squaring things, you just take the absolute value and add it all up. So that's a possibility. Again, pretty rare. Really, all that's doing is playing around with what sense, how do you want to measure distance between points in the space? So if you have a particular problem where you're like, I think given this data, I want to use something other than Euclidean distance to measure distance between points, fine, go ahead, do that. But normalizing your data and doing Euclidean distance is pretty good pretty much all the time. So that at least eliminates that question of what kernel to use. And once you've chosen that kernel, now there's only two parameters to optimize. So there's the size of the Gaussian, and this cost of constraint violation. So how bad is it to constrain that? So if that's your situation, very basic methodology to work with. Split your data into training and testing, because you want some sort of measure of how good this thing is going to generalize. You don't care if you use all your data as your training data, then you could always say, hey, look, I've got 100% accuracy. Not a useful measure. But split it into train and test. And then you're going to go through a whole bunch of different C and gamma values. And for each pairing, we're going to say, well, how good is it on that, given that parameter setting? And the way we're going to say how good it is, we're going to say, all right, we're going to take our training data. We're going to split the training data up again into actual training data and validation data. We're going to train up an SVM on that training data. We're going to evaluate it on the validation data. Say how accurate is it. And then we're going to do that a bunch of times. We're just going to repeat that with the same C and gamma value. Do it like 20 times. Do it 40, some number, because basically you don't want to know how, when you split it into this training and validation, you don't care about what the accuracy is on that particular split. You want to know, on average, how good is it? So we're going to do it a bunch of times. Do it a bunch of times, and then take the average accuracy, and that's going to be a measure of how good that particular C and gamma combination is. Then we just do that for all the different C and gamma populations that we want to look at, and out of all that, pick the best one. And then once you pick the best one, cool, okay, well, in order to make your final, your final thing that you want to say, okay, how good is this? Go ahead and train that again on all the training data. So, combine this training and validation back together again, or don't do this split. Train it on all of the training data, and that'll be your final thing, which you can then finally test on your test data and see what your accuracy is. So that's sort of standard methodology. That very similar methodology is going to be true for a lot of more complicated systems. This is really nice in that there's only two parameters we have to worry about. And so we can just do this exhaustive search and just try a bunch of different C and gamma values. So what's that actually look like? So here what I've done is exactly that measure. I've varied gamma across this axis here, and I've varied C across this axis here. And then for each of those data points, I'm doing this split into train and validation, evaluate how good it was on the validation, did that 40 times, took the average, that's what I'm plotting here. Awesome. And what this seems to indicate is, hey, pretty much any parameter setting up here seems pretty good. Be a little careful on this. If you ever go ahead and do this, and you generate your data, and you generate your plot, and it looks like this, you should not conclude, okay, then we just pick something in here. Instead, what you should conclude out of a plot like this is, wait a second, what happens if I keep increasing gamma? what happens if I keep increasing my cost? There's nothing magic about stopping at this line here. That just happens to be the particular values that I tried it on. Expand things out a little bit. Fine. Redo. There we go. Run it with more data. So I've now added a few more values of gamma this way and a few more things with the cost up here. Fine. Now I can see, all right, fine. If I increase gamma too much, then it starts getting really bad, which is what we expect. You make gamma too large, and it starts, you have these really, really tiny Gaussians. It starts turning into a lookup table. Increasing the cost up here, we keep increasing, and we're like, oh, okay. So this sort of trend continues. All of these values up in here seem to have pretty similar final accuracies. In theory, I could keep increasing this graph upwards. So sometimes when you increase the graph, it's really obvious, like, oh, okay, look, this stops working. In this case, as we're going up here, yeah, I could probably keep increasing this cost upwards. And probably what's a total possibility that could happen is it's just going to continue this trend. It's just going to look pretty much the same. It's just spreading out more. One reason to not do that with a support vector machine, as you increase cost, the compute time tends to go up for a lot of these optimization methods, just because it's working harder and harder to find something that really doesn't violate these constraints. So maybe that's a reason to stop doing this at some point, or it's just sort of, hey, look, I've extended this and I'm seeing the same pattern. I got to stop at some point. Cool. But we've got that. At the very least, at the very least, make sure for your gamma values you've increased them enough and decreased them enough so you can see, all right, it's bad for small gamma and it's bad for big gamma. There's something in the middle where it's good. That should always pretty much be the case. Cool. So I've got this data, and then I could probably pick anything in this range. I like picking sort of something that's sort of a centroid, so a center of mass of, all right, I got all these points here. I don't know, I might pick something like this. Maybe go up there. Doesn't really matter. These all have very similar performances. One thing you might want to look for is if I'm going to be picking a final model and deploying it somewhere, when that final model is being run, one thing that will affect how fast it is that final model will run is how many support vectors there are. Right? So I've got a lot of them. I've got to do a big sum. So one thing you might look at is the plot of the number of support vectors. And again, you can sort of see over here, all right, here's a situation where pretty much all of my data gets turned into a support vector. That's the lookup table part. But this is also indicating that, again, anything sort of vaguely in this range. Up here, we have fewer support vectors, fine, but that's also a region where the accuracy has dropped, so we don't want that. Unless, let me take that back. As an engineer, that might be a situation where you're like, hey, look, I really need to get as few, I got to make this algorithm run as fast as possible. Maybe it is more important to have it run more quickly with the fewer support vectors than it is to get that little extra bit of accuracy. All right, that's a trade-off that can be designed. In this particular case, it's probably more something in this kind of range. Seems to work pretty well. Okay. Cool. So yeah, that will be just a methodology that you'll just do that anytime, and similar-ish methodologies for other processes. But I like that this one's at least pretty standardized. If we do this to the data that we've been playing with, this is the result that we get. That's sort of, what is this? This is the gamma of 0.1 and a cost of 100. So that's gamma of 0.1, cost of 100. So that's around here in this decision surface. We get a certain accuracy, and that's as good as we can get on this data for this particular methodology. Yep. But it seems like a perfectly reasonable boundary line here. And that's what we got. All right, so that's what I wanted to say about support vector machines. It's worth, sort of the things that sort of can come up there. Support vector machines are great. If you can use them, try them, do them. The only worries, the only places that we're going to start having some worries. So scaling up to large data sets is a challenge. If you have thousands of data points, cool, fine, no problem at all. Start getting up to millions of data points, it's a bit problematic, and the problem is that K matrix. So when computing, I don't know where we've got it, way the heck back here, probably all the way back to the beginning of the presentation. Right. We've got to compute this sum here, which has every single possible combination. So we have to compute the kernel function on every pairing of our data. Okay. Which is, cheaper than computing, it's probably way cheaper than computing the features and then computing the dot product on every single combination of our data, especially if there's an infinite number of features. So fine, it's an improvement over that, but it's still expensive, especially if you've got a lot of data points. Yeah. So it's n by n, where n is the number of data points. That said, SVMs are so common that there's tons of tools out there that can approximate that or parallelize that or try to make that work better. But that it is definitely a challenge. Okay. Once you've got your support vector machine trained, though, the nice thing is you don't need this big giant matrix once you're deploying it in the field. You have some devices, okay, this is all trained up, and now I just need to do classification. Now the only thing I need to do is compute this, which only requires the particular singular values that I have. Right? So any of the data points that aren't a singular value, any of the data points whose alpha turns out to be 0, we throw them out, we can ignore them, we can just pretend they don't exist. When I get new data, all I have to do is compute this. But this is still linear in the number of singular values, right? So the number of singular values I have, that's, if I double my number of singular values, I've got to double my compute there. And in lots of situations, it just turns out that the number of singular values, if I double my amount of data, I probably am going to double my number of singular values. So that can be an issue, again, as data sets get large. That said, as data sets get large, you can also just try the linear version. Like, you don't need to do this whole kernel trick. You can go back to what we did like 2 lectures ago and just say, all right, I got lots of data. Maybe I'll compute a few features on it. But let's just, nothing says you have to use SVMs with these kernel tricks. So generally, most implementations, there's a linear version and there's a nonlinear version. The nonlinear is the one with the kernel. And in general, the linear version with no kernel, way faster, because, it's the same, you're going to end up with some weights, and you can do the dot product of my new data with the weights, right? That's fast. I don't need to have any of my, I don't need to store any of my data. It doesn't matter how many singular values I have, because with the linear version, I'm just getting some weights, because I just want the weights for the straight line that is dividing my data. So that's generally much faster, but will be in general less accurate than using my kernel. But that's also an indication. Try the linear version; it might work well. All right. So that's everything I wanted to say about support vector machines. But I do want to take this opportunity to go revisit regression. So far regression, so if we go back to that lecture, also a very similar structured algorithm. I'm still taking my input data, I'm multiplying it by some weights, that's producing some output. And then instead of that output being classified as, is it above 0 or less than 0, we're just simply saying, okay, no, that output is our output. Okay. And we also do have the option with regression of computing some features. Right? So instead of doing it on our raw data, we can compute some features on our raw data and then do regression. Okay. We showed that example with doing polynomial curve fitting. My input is one-dimensional, but then I'm going to compute a bunch of features, x to the 0, x to the 1, x to the 2, x to the 3, x to the 4, and then I find weights of those features that will add up to the data I want. That is polynomial curve fitting. That is regression. Anyway, so fine. When we talked about that, one way we could sort of write that is what we were trying to do is we were trying to find the weights that did the best job of doing fitting the curve. So that's what we're writing here. I'm taking my x values, I'm computing some features on the x values, and then I'm doing the dot product between that and my weights, and that's giving me a value. That's my output value, and then I can compare that output value to the desired output value. Okay. So this term here, that's our mean squared error. Right? I'm taking my square error, and then, well, I guess it's the sum of the squared errors, but whatever. So I'm just adding up that error across all of my different training examples. And then one of the other things we mentioned with a regression is, hey, sometimes you don't want to just do the curve fitting. Let's also minimize the weights. Interesting, that's the same thing that we're doing with support vector machines as well. That's kind of nice. But that's the form that we were talking about when we were talking about regression. Why am I bringing this up again? Well, let's sort of take a look at what we're doing here. So in the regression task, one of the things we were doing is we needed to compute this set of weights. I'm going to write it slightly different. I think one thing I'm going to do in the future is go through this whole course and just standardize all the notation. That said, it is kind of nice to be showing you just wildly different notations just because you're going to see that out there in the field. This is another way of writing, one way of writing what the solution to this is. Instead of switching to vector notation, I'm using matrix notation, where F is the big matrix of, that's what I called it when we talked about the class. I used F for this big matrix that was all the features by all of the sample points. I'm going to use, same equation, but notation that's a little bit closer to what we've been doing so far, or doing recently. So another way to find these weights, say we're finding this weights is, okay, this is my matrix. I'm using capital phi instead of F, just because I'm using lowercase phi to mean the features for a particular item. Everything else is all the same here. And again, this capital phi is this matrix of down this axis. We've got all the different data points, x1, x2, x3, x4. And then across here, I've got all of the features of that data point. Okay. And again, notation bad, these x's, these are themselves potentially vectors. This is the first data point that we're trained on. This is the second data point that I'm trained on, third data point, fourth data point. All right, fine. So what? Why am I doing this? The actual model, once we've trained this, fine, if I've got a new data point and I want to say what the output should be for that, fine, I take my new data point, I compute the features on it, and do the dot product with this set of weights that I've gone and learned. So what? Well, can we do the same weird thing to this as what we did with the support vector machines? So in the support vector machines, when we had the weights in this sort of form, we then ended up proving, hey, there's probably some way to write these weights. Actually, in the support vector machine case, it's really easy to prove that, yes, there is a way to write the weights as the sum of a weighted sum of sample points. Okay, we call this the representer theorem. It crops up in lots of places. It's not that surprising. If I have 50 different, let's say x is two-dimensional, right? If I have 50 different points in a two-dimensional space, yes, I can do a weighted sum of those 50 points to get any point in that space, right? That's not a surprise. In fact, any two data points in that space, as long as they're not collinear, or as long as they're not like right in the same line as each other, I can add them. I can do weighted sums of those to get points in that space. So it's not that big a surprise. We're going to apply that basic idea here. We're going to say, all right, let's say that those weights that we have, let's say that those weights can be written as a weighted sum of our feature vector. Okay, why would we do that? Well, okay, this equation here, that's what I said. All right, that's this thing here. Just put this inverted thing back on the other side. All right, this is the equation for finding the weights for regression. That's the equation for finding weights for the regression, and let's just make the assumption, which, unless I've got horrible data points, this is going to be true, that I can write this in that form. Fine, I can substitute that in. Now I can just, all right, copy this in through the parentheses. And now hold on a second. We're starting with a phi transpose here. We got a phi transpose here. This thing here, well, that's a scalar and that's an identity matrix. So that means I can safely cancel out all these phi transposes. And I'm left with this, which I can then pull out the alphas. And now I have a way of solving for alphas. And these alphas should be, fine. Once I have alphas, I can do alpha. I can take those alpha values. So that's going to be some scaling value, one scaling value per data point. I can multiply those by those data points, and that'll give me the weights. Okay. So very similar to what's happening in the support vector machine case. Although we just have alpha here, we don't have the alphas and the yi's. Right. Okay, fine. So we now have like a dual form for the regression. So we can, fine. And these should be identical. We've just done substitutions. We've just done math on it. So it should just be a different way of getting the same result. Right, because once, once I've got, sorry, just to be a little bit clearer here, once we've got these alpha values, what do we do with them? Well, we do have to, if I've got a new data point and I want to know what the predictions are, I'm supposed to do this computation here. I'm supposed to take the features of that new data point and do the dot product with omega. So, but if omega is this thing, if omega is just a weighted sum of my features, then that means I can rewrite this here. So when I've got a new data point, I just have to do the dot product. I just have to compute features on that, and then do the sum of, do the dot product of my new features with the features of all of my data points, and then have some weighted sum of those. That should all be mathematically identical. All right, this bit over here is looking kind of familiar. And maybe you can sort of get a sense of where we're going here. And indeed, if we go and look at this matrix here, this phi transpose thing, what's that? Well, that ends up being an n by n matrix where each element is the dot product of the phi's for each of my points in my training data. That's pretty familiar. That's just, we had to make that matrix in support vector machines. That's the dot product of everything with itself. That's the big K matrix. So what we're indicating here is we can, with regression, do exactly the same trick that we did with support vector machines. We can use the kernel trick. I can do regression in some other space, and the only thing I have to do is build up compute these kernel functions as my measures between data points. Let me say that again. So I'm going to do this. So in order to find my alpha values, I need to compute the kernel function on all my data points. And my kernel function is going to be, if we were doing it the long way, it would be the dot product of my features between the data points. But then what we said is for particular feature sets, I can just simply say compute the Gaussian right there. Right? I can just do x1, x1 minus x2, norm of it, e to the minus gamma that. and that'll give me this value, and I don't have to compute the features. Same thing over here. I can just do k of xi and x, and I don't have to compute the features. So I'll still be doing regression in the high-dimensional space, in whatever this feature space is, but I never have to compute that high-dimensional space. Same trick. For clarity, I will also point out, and just sort of being really careful here, this matrix here, phi transpose, is very different from this matrix here, phi transpose phi. Okay, the phi transpose, that's number of training points by number of training points, because it's we're computing the kernel function on every pair of those, or equivalently, for each pair, compute the features, do the dot product between the features. Whereas this one, this phi transpose by phi, that ends up being number of features by number of features. Okay. In lots of, if I have lots of training points and very small number of features, all right, then I probably want to do it, if both of these things do the same thing, get the same result, then I would probably do it this way. But if I'm working in an infinite number of features, then this is going to be the smaller approach. Okay. Okay, summary of all that. For regression, we can do it the normal way that we talked about in the class on regression, where we start with x, we compute the features on x, right? And then we go ahead and build a big matrix, add something on the diagonal in order to regularize it, invert it, do this multiplication, that gives me my weights. And then once I've got my weights, if I've got a new data point, I compute features on that data point, do the dot product with the weights, that gives me my new data point. Okay? That's what we did in the class on regression. For here, I'm pointing out that, hey, alternatively, I could do this math. I'm still starting with x, still compute a bunch of features on those x, and then I do this math. That gives me alpha, and that's a big giant vector with a different value for every single one of my my data points in my training set. All right. Once I've got that, I could then predict by saying, oh, okay, I've got a new data point, compute its features, do the dot product with all the points in my training set, scaled by alpha, add that all up, that gives me y. Those two things are identical. And indeed, just as an example, let's actually, if we actually did it for something similar to what we saw in the previous class, here's my set of features. So x in this case is one-dimensional. The blue dots are my training points. This is my set of features, and I've just set the regularization parameter to, what is that? 1, 2, 3, 4, 10 to the minus 6. Anyway, if I do that, and I use either of these two methods, these methods are mathematically identical. They'll give me the same answer, and they do indeed give me the same answer. Okay. Which one's more efficient? Well, in this particular case, this is going to be way more efficient because it's inverting. This matrix here that ends up getting inverted is a 5 by 5 matrix, whereas down here it's a 8 by 8 matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, this is a 10 by 10 matrix for this one. Right. Fine, you could do it either way, and of course, the reason why you might want to do it this other way as well, if you want to have an infinite number of features and you don't feel like computing all infinity of those features, then, all right, we do this matrix where k is I compute the kernel function on every single pair, and I can compute alpha, and then I go ahead and compute my kernel function on my new data points coming in, scaled by alpha, and I'll get that. And that will effectively do regression in an infinite dimensional space, but I don't actually have to compute the infinite dimensional space, I just have to compute k. As an example, we're going to do it with, do regression with a Gaussian kernel. Fine, that's our k function, which is this, which is pretty easy to compute. The equivalent feature space that's doing, as we mentioned in previous class, there's this just infinitely long sequence of features that's effectively being computed here. And if we go ahead and apply that, again, we have sort of things we can play with. We can either write it as gamma, as we're doing here, or we can think of that gamma as 1 over 2 sigma, where sigma is the width of the Gaussian that's being added there. So here we are with sigma is 0.1. I can make that sigma smaller. It's fitting the curve pretty well. And I can, of course, make sigma larger and larger. Okay. Again, we're just doing curve fitting now, but that's this sort of general technique is going to work fine. And it is worth noting, like, doing this sort of curve fitting, it's very similar to the classification stuff we're doing. The classification is just our output is either 1 or -1, or 0 or 1, or whatever our classes are. Here we have just a little bit more of a continuous output. This is okay. All right, so we have this data set. One thing we can, of course, that maybe helps visualize why this is happening, why these curves look like this. We want to sort of understand what's going on. We can also just directly plot what this kernel looks like. So what we're doing here is we're plotting each of these functions up here, the things that are going to get weighted and added up in order to produce this curve. So this curve here is produced by doing a weighted sum of these shapes. Okay, that's another way of expressing exactly what's being said with this equation. And as we adjust gamma, or equivalently adjust sigma, because gamma is 1 over 2 sigma, or sorry, gamma is 1 over 2 sigma squared, then, all right, over here, fine, we've got these very, very, very peaked Gaussians. This becomes very similar to the lookup table, right? And the lookup table version of a support vector machine. And then as we make sigma larger, these are going to be spread out more. It's harder to exactly hit the points. We don't need to exactly hit the points because the regression has a, the regression does also have a regularization term in it. So it's also under pressure to keep the magnitude of the weight small. And we get this nice little smooth thing there. And yeah, those are very, very, very wide Gaussians now. So of course we can't do a good weighted sum of them to get these points. All right. So all that. So this kernel trick is more general than just support vector machines. It can also be applied to regression, a few other things. Like any sort of the point of this situation is we can use an infinite dimensional space without actually transforming that data. Whereas for support vector machines, regression, those are probably the main cases. There's lots of other interesting research work to be done where people are working with kernels and looking at their applications in different domains. But as far as sort of practical application for right now, that's sort of standardized, sure, those are the two that really pop out. Support vector machines being you definitely wanted to at least try them with support vector machines. Relatively common to also try them with regression. For support vector machines, yeah, use radial basis functions. Use the Gaussian, optimize the cost, optimize gamma. For regression, same situation, really. You can. It's a similar constraint. Yeah, if you want to use the radial basis functions and then optimize gamma and sigma, or sorry, optimize lambda and sigma. Lambda being the regression term or the regularization term in the regression, and sigma being 1 over 2, or gamma being 1 over 2 sigma squared. Again, they're nice and straightforward to do a parameter search for. Drawbacks, yeah, pretty much the same drawbacks that we've been talking about. The K matrix is big. It's n by n, which is better than infinite by infinite, and we effectively get an infinite number of dimensions out of it. That's still pretty big. Yeah, 10,000 data points, maybe 100. Yeah, that's sort of an upper limit, but it can work very, very well. And you even get away with things like, oh, if I have 1 million data points, well, I'll put 1% of them in my training data and 99% of them in my test data, and now I only have to work with 10,000 data points. So you can play games like that. And even though we've sort of introduced this weird kernel version of things, it is also worthwhile to, hey, for both regression and support vector machines, try the linear version. It works a surprising amount of the time. Maybe you don't need any of this extra fancy stuff. All right, so that's it for the kernel trick stuff. And in the next lecture, we will go on to start actually talking about more this whole neural network thing, which is apparently pretty important for AI these days. So we will see how that goes. Thank you very much, and we'll see you later.